Hi everyone, this is Maverick Paul, the chemistry guru. What we want to do today is we want to discuss how to draw the Zwitterion of an amino acid and how to determine the isoelectric point of an amino acid given the pKa values for my functional groups in this amino acid. So let us use these three amino acids as an example so that we have a few examples to practice all these ideas involving drawing Zwitterion, calculating isoelectric point. So the first amino acid that we have is alanine. The structure is given here and the pKa values are all given. Later we will refer to them in detail. Cysteine. Cysteine, you notice my R group actually has a functional group that has a pKa value. So later we will also comment on that. Lysine. We have three pKa values. Again, I'll have a functional group inside the R group that has a pKa value. So as mentioned, what we want to do today is there are two things. First thing is for each of these amino acid, we want to learn how to draw the Zwitterion and we want to determine the isoelectric point, calculating the isoelectric point for each of these amino acids. So let's take a look at the first amino acid, alanine. Now alanine, the structure is given here. The pKa value for your alpha acid is 2.35. Let's call this pKa1. Then the pKa2 for your alpha amino group, it is 9.87. So let's call this pKa2. And my R group, it doesn't have an acidic functional group or alkaline functional group. So I will only have two pKa values to worry about. So we want to do two things. First one is I want to draw the Zwitterion. And let's take a look at how we should do that. Now, we should be familiar with the concept of a Zwitterion. A Zwitterion, essentially, it is a charged species, but it is overall neutral because I will have one part of your amino acid being positively charged, another part of your amino acid being negatively charged. So a Zwitterion is overall neutral. How do I consider drawing this Zwitterion? One way that we can use is we just consider the reaction between the strongest acid and the strongest base. So effectively, what is happening is the acid will donate the proton and the base will accept the proton. And because of that, we'll have a species which is positively charged and a species that is negatively charged. Overall, this guy will be neutral. So involving alanine, this is fairly simple because very nicely, I only have one acid and I have one base. So the acid obviously will be the proton donor. The base will be the proton acceptor. So there's only one acid reacting with one base. Your COOH will lose the H+, it becomes COO-, and your NH2 will gain a H+, it will become NH3+. So the Zwitterion for your alanine will look something like this. I'll have a NH3+, CH3, and a COO-. So Zwitterion involving species where the R group is neutral, that means there's no acid or alkaline functional group present in your R group, is actually fairly straightforward. I just need to transfer the proton from the alpha acid to my alpha amino group and I'll be able to draw this Zwitterion very, very easily. Now the next thing is I want to determine the isoelectric point. How do I calculate the isoelectric point? Now the idea that we can use is this. First thing is I want to determine the pH range for each of my functional group. Now for this amino acid, it seems a bit unnecessary for us to do that, but later we want to apply the same idea to amino acids where I have three functional groups with three pKa values, then this idea will be applicable. So what we want is we want a concept that I can consistently use for all my amino acids, regardless of whether I have only two functional groups with a pKa value or three functional groups with a pKa value. So let me run through this idea. We want to determine the pH range for each of my functional group. So what we want to determine is if my alanine or my amino acid exists in this form, what must the pH range be with respect to each of these functional groups? Alright, so let's consider this part by part. Now, if I look at my alpha acid group, my alpha acid actually has reacted off to form COO-. And what this means is the pH of the solution with respect to your alpha acid, the solution has to be alkaline with respect to your alpha acid. That's why at that particular pH, my alpha acid thinks that the solution is alkaline with respect to me, and if I'm an acid, I'll respond and I'll react to form COO-. So this tells me that since the acid is reacted off to form the conjugate base, solution is alkaline with respect to your alpha acid, and therefore the pH of the solution must be greater than pKa1. Now how about my alpha amino group? You notice for my alpha amino group, it is converted to NH3+, so my amine takes part in the reaction. And what is the pH range where my amine will take part in the reaction? The solution must be acidic with respect to my amine functional group. So the solution is acidic with respect to amine, and this will mean that the pH of the solution must be smaller than pKa2, lower than the pKa value for alpha amino group. So what we want to do is we want to determine the pH range where my amino acid will exist as a Zwitterion. Then the isoelectric point will be the midpoint of this pH range, because by right we know that the range where your amino acid will exist in this form as a Zwitterion, this is the range, right? We've already mentioned pH is greater than pKa1, then pH is smaller than pKa2. What we can do is we can put everything into this number line. Again, if there are only two pKa values, this number line is not really necessary because it is very easy for us to do comparison. But the significance of this later when we draw the Zwitterion for my subsequent two amino acids and determining the isoelectric point for the other two amino acids, if I have three values, then things becomes a little bit more complicated. So using this number line actually makes it easier for us to visualize the pH range. So if I look at the first thing, I know that pH must be greater than pKa1. So my pKa1 is here 2.35. So this is the range here. Start from pKa1 and it has to be bigger than pKa1. Then involving pH smaller than pKa2, my pKa2 is here 9.87. The pH must be smaller than pKa2. So at this point, I draw an arrow towards the left hand side. And what is the range that we have? I know that the range where your amino acid will exist as a Zwitterion is this range here, between 2.35 to 9.87. So this is actually the whole range where your amino acid should exist as my Zwitterion. Actually, this range is the range where your amino acid will exist predominantly as a Zwitterion. That means majority of it will be the Zwitterion. So what we want is we want the instance where 100% of my amino acid will exist as a Zwitterion. So by definition, that point where my amino acid exists 100% as a Zwitterion, that will be my isoelectric point. So where is my isoelectric point? Very simple, it is midpoint of this pH range. So basically what we do is I add up the two values, divide this by 2. The isoelectric point for my alanine is 2.35 plus 9.87 divided by 2, 6.11. So at pH 6.11, 100% of your alanine will exist as a Zwitterion. So just to clarify, isoelectric point, it is the midpoint involving this pH range. At isoelectric point, when pH is 6.11, 100% of your amino acid exists as Zwitterion. This range here from 2.35 to 9.87, the Zwitterion will be the predominant species. So that means I will have a Zwitterion and another species, but majority of it will be the Zwitterion. So just to clarify between isoelectric point and this range here. So this is for alanine amino acid. Now next, let's consider cysteine. Now cysteine is a little bit more interesting because my R group, I will have a functional group that has a pKa value. So let's take a look at that. My alpha acid pKa1 is 2.05. Then my alpha amino group, let me call this pKa3, is 10.25. I have my SH functional group. Now SH group, it is a proton donor. It is acidic in terms of nature because it can donate H plus to form S minus. pKa2 is 8.00. Now what is interesting involving this pKa2 equals to 8.00 is, even though this pKa2 is greater than 7, but it doesn't mean that this is a base. Whether this is acid or base, we have to look at the functional group, not just purely based on pKa value. So we have to be careful with that. this is my SH. SH should be able to donate H plus to form S minus, and this is an acid, pKa 2, 8.00. So same thing, we want to determine the Zwitterion. I want to calculate the isoelectric point, taking note of the ideas that we've talked about previously. First thing is, how do I draw my Zwitterion? Now remember, the idea involving drawing Zwitterion is, overall this is neutral. It is charged, positive charge somewhere, negative charge somewhere, but overall this is neutral. So how do I draw the Zwitterion? The easiest way is, we take it that this is an acid-base reaction between the strongest acid with the strongest base. In terms of functional group wise, you notice I have two acidic functional group. My alpha acid is acidic, obviously. SH functional group is also acidic. This is also a proton donor. I'll have two acids. And amine group, alpha amino group, this is a base. So if I want to form my Zwitterion, what I'll do is I'll use the strongest acid reacting with the strongest base. Now if you think about it, it makes sense, because if I want to have an acid-base reaction and I have only one base, who will be the acid that is reacting with this base? It has to be the stronger acid, because the stronger acid has a greater tendency to donate its proton. So the stronger acid will always take part in acid-base reaction first, correct? So in this case, I have one base, so the base has to take part in the reaction because there's only one base. Now between the two acids, which of these acids should be the proton donor? The stronger acid has to be the proton donor. So when I have an acid-base reaction to form a Zwitterion, the reaction should be between strongest acid versus my strongest base. So my base, NH2, will take part in the reaction to form NH3+. Between my two acids, who is the stronger acid? My alpha acid is the stronger acid. So I should be converting this COOH to COO-. So my Zwitterion should exist in this form. NH3+, CH, CH2SH. My SH functional group doesn't lose the H+, and COO-. So this is my Zwitterion for cysteine. Now, the next thing is I want to determine the isoelectric point. Now, determining isoelectric point, what we have to do is I have to look at the pH range for each of these functional group. Now I have 3 pKa values, so we have to consider this part by part. This is my Zwitterion. So we want to determine, okay, what is the pH range so that my amino acid will exist as this Zwitterion. So let's look at this functional group by functional group. If I consider my alpha acid, now you notice for my alpha acid, it takes part in the reaction, correct? It is converted to COO-. So this will mean that the solution is alkaline with respect to your alpha acid, and therefore the pH has to be greater than pKa1, has to be bigger than 2.05. Next, how about my pKa2? Let's look at pKa2. Now pKa2, remember this is an acid functional group. You notice this SH, it doesn't take part in acid-base reaction, it remains as an acid. So this would mean that the solution is acidic with respect to this functional group. Because acid is supposed to react with alkaline solution, it doesn't react with acidic solution. So if my acid stays put, it doesn't donate the proton, it will mean that the solution is acidic with respect to this functional group, and therefore the pH has to be lower than pKa2. So the pH will be smaller than 8.00. Now if I consider my alpha amino group, my pKa3 is 10.25. You notice it takes part in the reaction, converted to form NH3+. So this will mean that the solution is acidic with respect to the base. If my amine takes part in the reaction, the solution is acidic with respect to your amine, and therefore the pH will be smaller than pKa3, pH is less than 10.25. So these are all the ranges that we have, and we want to combine them together, and we want to work out the pH range which is consistent with everybody. So this is where using this number line will be useful. Otherwise, I have 3 pH ranges. Maybe it's a little bit confusing. So let's put this into my number line. So my pH is here, and I have all my pKa values. pKa1, 2.05. pKa2 is 8.00. pKa3 is 10.25. And let us consider the range that we have here. First one is pH must be bigger than pKa1, greater than 2.05. So pKa1 is here, greater than 2.05. Next, pKa2, 8.00. We have deduced that your pH must be smaller than pKa2. So my pKa2 is here, and pH has to be acidic with respect to your pKa2, so smaller than pKa2. Then finally, your pKa3, 10.25, which is here. We know that pH is smaller than pKa3, so pKa3 is here, and the pH is smaller than 10.25. So what we want is we want the range where it is consistent with all these three information. So where is this range? This range will be here, correct? You notice it is between 2.05 and 8.00. This region here, this highlighted region here, is where all of them are consistent. Your pH is bigger than pKa1, smaller than pKa2, smaller than pKa3. So the pH range where your amino acid will exist predominantly as my Zwitterion. That means majority species or the major species will be my Zwitterion is this range here, 2.05 to 8.00. And if I want to calculate the isoelectric point, the pH where your amino acid will exist as Zwitterion 100% will just be the midpoint of this pH range. It will just be 2.05 plus 8.00 divided by 2, 5.02. Now finally, let's look at lysine. Hopefully we are getting the hang of it. Now lysine, I will have 3 pKa values. My alpha acid pKa1 is 2.18. My alpha amino group pKa2 is 8.95. And inside the R group, I actually have an amine function group. pKa3 is 10.53. So same thing, let us try to draw the Zwitterion first. We want to apply the exact same idea. How do I deduce my Zwitterion? Strongest acid react with my strongest base. So for this amino acid, I have one acid functional group, I have 2 bases. So the idea is my acid must take part in the acid-base reaction, correct? Because there's only one acid. So between the 2 bases, which base should take part in the reaction? Of course, the stronger base should be the one that is reacting first. That's why this idea, strongest acid reacting with my strongest base to form my Zwitterion. So my acid has to take part in the reaction. COOH becomes COO minus. Between my 2 bases, the one with the bigger pKa value will be the stronger base. So who is my stronger base? This R group amine is my stronger base. NH2 becomes NH3+. My alpha amine is not going to do anything because it is the weaker base for this amino acid. So my Zwitterion will be something like this. NH2CH. I have an R group with an NH3+ and a COO minus. My Zwitterion will look something like this. Next, let us learn how to determine the isoelectric point. Now, determining the isoelectric point is the same thing. First thing I have to determine, okay, if my amino acid exists in this form, what is the pH range for my amino acid to exist something like this? So we have to consider functional group by functional group. I have to deduce since the functional group respond or don't respond, whether it reacts or not. I can decide whether the solution is acidic or alkaline with respect to that functional group. So the first one involving my alpha acid, it has reacted, becomes COO minus. So the solution has to be alkaline with respect to your alpha acid. pH is greater than pKa1. Alright. How about my alpha amino group? Alpha amino group, you notice it doesn't respond. It just exists as it is. There's no change. So if your amine doesn't take part in the reaction, it will mean that the solution is alkaline with respect to your amine. Because the solution is alkaline with respect to amine, then the amine is not going to do anything. It just exists as NH2. If the solution is alkaline with respect to your alpha amine, then the pH must be bigger than pKa2. pH is bigger than 8.95. Now finally, if I consider my R group amine, it has reacted to form NH3+. So if my R group amine takes part in the reaction, the solution must be acidic with respect to your amine functional group. pH will be less than pKa3. So once we have this range, then what we can do is, again, I put it into the number line. Makes it easier for us to figure out what is the range that we want. So the range will be here. Same thing, my pH line is here. pKa1, 2.18. pKa2 is 8.95. pKa3 is 10.53. So the first thing that we have determined, pH must be bigger than pKa1. So pKa1 is here. I draw one line towards the right hand side. pH must be bigger than pKa1. Second thing, pH must be bigger than pKa2, alkaline, with respect to your alpha amino group. So pKa2 is here, 8.95. pH is bigger, so draw one line towards the right hand side. And finally, pH is smaller than pKa3. So pKa3 is 10.53. pH is smaller than that, so I draw one line towards the left hand side. So you notice once I have all these lines drawn out, using this number line, I think it is significantly easier for us to determine what is the range that is consistent with all this information. You notice my range is here between 8.95 to 10.53. So this pH range, 8.95 to 10.53, it is the range where your amino acid will exist predominantly as a Zwitterion. But what is my isoelectric point? The isoelectric point, same thing, will just be the midpoint of this pH range. So the isoelectric point for lysine will just be 8.95 plus 10.53 divided by 2, and I'll get this isoelectric point 9.74. Alright, so that was the discussion involving learning how to draw the Zwitterion for my amino acid and learning how to calculate the isoelectric point for my amino acid if you're given the pKa values for that amino acid. If you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.